So in the last session, we have been talking about the multiplicity of a zero of a polynomial. We haven't yet defined the separable extension, but before that we need to prove one more result, which we already stated earlier. The result is if E is a finite extension of E of F, then the index of E over F divides the degree of index over F. We are going to use a result which we proved earlier. That is, if K is a finite extension of E, which is a finite extension of F, then K over F, the index of the degree of K over F is equal to K over E times E over F. And similarly, index also is like this. K over F is equal to K over E times E over F. Proof is very simple. So we'll first assume that E is a finite extension of F, and that implies there exists alpha 1 alpha n in F closure such that F is a subfield of F of alpha 1, which is a subfield of F of alpha 1 comma alpha 2, then it's a subfield of F of alpha 1 alpha n, and that is equal to E. So in this case, alpha I is algebraic over F of alpha 1 dash dash alpha I minus 1. So there is a irreducible polynomial. Let P of x equal to alpha I, irreducible polynomial of alpha I over F of I minus 1. And has ni zeros with the multiplicity Vi. All ni zeros have same multiplicity, and that is Vi. Then the degree of F of alpha 1 dash dash alpha I over F of alpha dash dash alpha I minus 1 is equal to ni Vi. Because there are ni zeros, each of them have Vi as a which of them have multiplicity of Vi. But in the case of index, F of alpha 1 dash dash alpha I over F of alpha 1 dash dash alpha I minus 1, that is going to be just Ni. Because here it is the automorphism. So each of these Ni conjugates should map to one of its conjugate. So it should be Ni. Doesn't matter how many occurrences of each zeros are there. So now we apply that rule. So we have here E over F is equal to actually E over F of alpha 1 dash dash alpha n minus 1 times F of alpha 1 dash dash n minus 1 over F of alpha 1 dash dash n minus 2 dash 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 here F of alpha 1 over F. And that is actually equal to pi of ni vi, I from 1 to n. And what about the index? Same as, but it's an index. It's instead of replace index degree by index. F of alpha 1 dash dash alpha n minus 1 times F of alpha n minus 1 over F of alpha n minus 2 dash dash, this is actually curly brackets, this is also a curly bracket, and this is a curly bracket here, and this is a curly F of alpha 1 over F, and that is equal to pi of I 1 to n ni. So definitely that implies the index of F divides the degree of F. Now let us define a separable extension. Definition. I'm going to assume that E is a finite extension. E is a finite extension. Then extension of E, extension of F. Then E is separable over F if the degree is equal to the index. Or in other words, another flavor of this definition is if alpha belongs to F closure and alpha is separable over F if F alpha is separable over F, because it goes back to this definition, and that means the index of this over F is equal to the degree of F alpha over F. Then another flavor is an irreducible polynomial f of x in f of x is separable if every zero of f of x is separable. it goes back to this definition. We'll give you an example. Let's take Q of root 3 is our E and F is equal to Q. Here E over F is equal to Q of square root of 2 over Q, and that is equal to 2, which is the same as E over F. So Q of cube root of 3 is separable over Q. Same as square root of 3 is separable over Q. That is the second definition. And the third definition is the irreducible polynomial, that is x square minus 3 is separable over Q. We have not included the multiplicity in the definition of the separable extensions. Now let's see how the multiplicity is affecting the separability. So an element alpha belongs to F closure is separable over F if f of alpha over f is equal to f of alpha, index is equal to degree. That is a second definition of the separability. So let P of x is equal to irreducible polynomial of alpha over f be the irreducible polynomial over of alpha over f, and let V be the multiplicity of alpha. Multiplicity of alpha, and let n be the number of distinct zeros of P of x. Then the index of E over F, or F alpha over F, is going to be n, and the degree of F alpha over F is equal to nb. So if you want alpha to be a separable, then if alpha is separable over f, then the index is equal to I'm sorry, is equal to the degree of alpha. And that implies v is equal to 1. And when v is equal to 1, if you go back, you'll see that alpha is separable. So an element alpha is separable over f if and only if its multiplicity is 1. Similarly, if you extend this definition, this condition to an irreducible polynomial, an irreducible polynomial is separable over f if and only if all of its zeros have a multiplicity equal to 1. If one of them is of multiplicity 1, then every other zeros also will have the multiplicity 1 because they are conjugates. So this is the necessary and sufficient condition for an element and an irreducible polynomial to be separable. We'll do another result theorem. If E is a finite extension of f and K is a finite extension of E, then K is separable over f if and only if E is separable over f and K is separable over E. A very simple proof. Given that f is a subfield of E, which is a subfield of K, and all are finite extensions. This implies K over F is equal to K over E times E over F, and the index K over F is equal to K over E times E over F. If K is separable over F, implies K over F is equal to the index of K over F. and that means K over E times E over F is equal to the index K over E times E over F. See, when this happens, this have to be equal. Why? See, let us assume that this is 12 and this is 3 and 4, and this is also 12, but you don't need to have 2 and 3, it could be 2 and 6. But this is not possible because then, see, in any case the index divides the degree. So in this case 2 does not divide 3. It has to be 3 and 4. So that is what I'm going to write here. Since the degree K over E divides K over F, and E over F divides E over F, what does that mean? That means K over the degree of K over E is equal to the degree of the index of K over E, and the degree of E over F is equal to the index of E over F. And that implies we are assuming that K is separable over F. So this means that K is separable over E, and this implies E is separable over F. That is one side of the if and only if. The other side is, let K is separable over E and E is separable over F. That implies K over E is equal to the index K over E, and the degree E over F is equal to the index E over F. And that is equal to, that implies K over F, that is equal to K over E times E over F, and that is equal to K over index K over E times E over F, and that is nothing but the index of K over F, and that implies K is separable over F. We'll do another result. Let E be a finite extension then E is separable if and only if every element in alpha is separable. F. So let us assume that let E be a separable extension. A separable extension of F, and alpha belongs to E. This implies F is a subfield of F of alpha, which is a subfield of E, and that implies F alpha is separable over F, and that implies alpha is separable. That is simple. Now let us assume that let every element of E is separable. And E is a finite extension. Then there exists alpha 1 dash dash alpha in F closure such that F is a subfield of F alpha 1, which is a subfield of F of alpha 1 comma alpha 2, F of alpha 1 alpha n, and that is equal to E. Now each alpha I is separable over F. And that is assumption. So that implies alpha I is separable over F of alpha 1 dash dash alpha I minus 1, because alpha I is separable over F means what? That means the irreducible alpha I has a multiplicity of 1. That implies the irreducible polynomial of alpha, or let us write like alpha I is a 0 of the irreducible polynomial of alpha I over F with the multiplicity 1. So that definitely implies, or we'll take one more step here. And here, irreducible polynomial of alpha I over F of alpha 1 dash dash alpha I minus 1 divides irreducible polynomial of alpha I comma F. because this is an extension of f. That implies alpha I is a zero of irreducible polynomial of alpha I comma f of alpha 1 dash alpha I n minus 1 with multiplicity 1. It cannot go beyond 1. And that implies alpha I is separable over f of alpha 1 dash dash alpha I minus 1. And what does this mean? This means that f of alpha 1 dash alpha I minus 1 of alpha I is separable over f of alpha 1 dash alpha I minus 1. And what is this? This is nothing but alpha 1 dash dash alpha I. You are joining alpha I to this field is separable over f of alpha 1 dash dash alpha I minus 1. So here what I am saying is alpha f is separable over f of alpha 1. F of alpha 1 is separable over f of alpha 1, alpha 2, etc. It's f of alpha 1 dash 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 f of alpha n minus 1 is separable over f of alpha 1 dash 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 alpha n, and which is equal to e. So that implies e is separable over f because of the earlier result. Meaning if k is separable over f, if and only if k is separable over e and e is separable over f. So that is a result we are using here.